Whether you're using ChatGPT, Claude, or Gemini, you are interacting with the exact same underlying architecture. Despite their different interfaces and training data, the frontier AI systems we use today share a single structural DNA. That architecture traces back to a specific origin point, a 2017 paper published by 8 researchers at Google and the University of Toronto, titled "Attention is All You Need." This document introduced a mechanism that allowed AI to move away from reading one word at a time. It enabled models to utilize the full processing power of modern hardware, which had been the primary hurdle for the generative AI models that followed. To see why that shift was necessary, we have to look at the flaw of the old system. Before 2017, AI models like recurrent neural networks processed language exactly the way humans do, sequentially. They read text one word at a time, strictly in order. This creates a physical limitation. Because the system can't process word 4 until word 3 is finished, it operates slowly. A single computational node does the work, while thousands of parallel GPU cores sit completely idle, waiting for their turn. Sequence also causes memory loss. By the time the model reaches the end of a long paragraph, the mathematical signals from the earliest words have often faded from the system's memory, destroying the long-range context needed to understand the text. Passing data sequentially across hundreds of steps creates extreme mathematical instability. These signals tend to either vanish entirely or multiply until they exponentially explode, crashing the calculation. Building faster sequential readers wasn't the answer. To scale AI, engineers needed a machine capable of absorbing the entire page all at once. The fix was the transformer. It replaced sequence with a mechanism called attention, allowing the model to look at all words simultaneously. The first step is translating human language into math through a process called embedding. The model converts every word into a vector, a list of 512 numbers. This turns abstract vocabulary into physical coordinates in a geometric space, where words with similar meanings sit close together. But if the machine sees all these coordinates at the exact same time, it has no way to know the sentence order. To an attention mechanism, dog bites man and man bites dog appear identical. The transformer solves this using positional encoding. It layers intersecting sine and cosine waves to stamp every single word with a unique mathematical location signal. By converting vocabulary into numerical vectors and stamping them with spatial coordinates, human grammar becomes pure, parallelizable math. This allows for self-attention. This is the process where every word simultaneously looks at every other word in the sentence to decide exactly which ones matter to its own meaning. Pacing picks up slightly. It works through a 3-part matching game. Each word generates a query, which asks for the context it needs. It also generates a key, advertising the context it has to offer. And finally, a value, which holds its actual meaning. This diagram shows the scale-dot-product attention flow. The model multiplies the queries against the keys in the matmul step, then converts the results into percentages using softmax. This calculates exact relevance scores, isolating only the required context. This diagram details multi-head attention, where the transformer runs 8 of these processes in parallel. Each head looks for different relationships. One maps grammar, another tracks tone, and another hunts for long-range references. Self-attention acts as a memory retrieval system. Any word can instantly grab context from anywhere in the document, bypassing the sequential degradation that hindered older models. This chart shows the full transformer model architecture. We can see how these sublayers fit into the macro structure of 2 main towers. The left tower is the encoder. It stacks the attention block 6 times, tracking the flow upward. With every pass, it reads the input prompt and deepens its understanding of the context. The right tower is the decoder, responsible for writing the output one word at a time. It uses a masked attention layer, which ensures the system only looks at words it has already written, preventing it from looking ahead at words it hasn't generated yet. These central arrows form a bridge known as cross-attention. Before generating a new word, the decoder peeks back at the encoder's context map to mathematically determine the most accurate next step. This twin tower setup separates the act of comprehensively reading a complex prompt from the step-by-step drafting of the response. Upon its release in 2017, the transformer outperformed existing translation benchmarks. Because it allowed GPUs to run at full parallel capacity, it trained in just 3.5 days, a fraction of the previous cost. With the sequence bottleneck gone, researchers realized they could scale the models significantly by adding more data and compute power. This paper established the lineage for modern AI, from BERT in 2018 to the GPT series and multimodal systems like Claude and GPT-4. The transformer provided the high-speed structural foundation for nearly every frontier model in use today. By moving from human-like sequence to parallel mathematical attention, the transformer didn't just solve language translation, it provided a new path for how machines process information. In 2017, it turned out that attention really was all they needed.